Hello, gentlemen. It ends up that I've been implementing a lot of allocators and containers in the last couple of weeks. I don't really know why. I don't have much of a use for them right now, but I'm pretty sure I'm going to be using these in most of my programs going forward. But this time I implemented an Arena Allocator here called Junk Allocator. You may have seen a previous video where I implemented this block allocator, which I'm not going to talk about in this video, but the code is on GitHub. I saw a couple people give it stars, so if you're using that, or if you used it to copy some of its code or whatever you were doing with it, go and look at the changes, because the old version had bugs and crashes in it. Okay, so an Arena Allocator is basically an allocator that's going to give the user a large block of memory. Usually the user is going to be responsible for allocating this memory and then deallocating this memory. We do that here in the form of this create arena and destroy arena function. Okay, it's just a big block of arbitrary memory, and the idea is that there's an offset stored into that memory, and you basically just increment that offset and return the pointer whenever somebody allocates into your Arena Allocator. So when you allocate into an Arena Allocator, right, and the offset is 0, it's going to return you just the raw pointer, and then you can just place your type at that address, and then it's going to increment the point or the offset by the size of the type, and then you're going to be at the next address, and the next time somebody allocates, it will give you that new address. So it's really dead simple. It's actually so simple that it can be almost as fast as allocating on the stack. I don't maybe it even is the same speed. I don't know. I think the best way to demonstrate what is the use for an Arena Allocator is kind of to look at some test code. So right here, I have an example of something that you might do. Maybe you are a game engine dev and you are loading in a vector of vertexes, right? And so you want to find each unique vertice, and an elegant way to do that is to use standard unordered set. Here I'm using standard set to have it print better. It's going to print a little nicer. We get a... Oh, let me comment out this code right here. Okay, so yeah, you're going to see that this gets us all of the unique integers in the vector, right? So for example, let's see, there's no 10, there's no 9 in this vector. So this set contains all the unique vertices or integers that were in this vector, right? So there's a couple of problems here. Standard set will dynamically allocate basically a node structure, which is, I think, similar to a linked list structure. It's your type and a pointer, maybe another pointer, I don't know. And it's not going to be cache local, and it's going to be a bunch of new and delete calls, right, for a bunch of system calls. So that sounds slow, and you might think, well, you can just implement your own set, right? And so your own set will be a flat set, and I implemented a flat hash map, so I'm pretty sure I could just modify it to be a flat set. But your flat set would still have the problem that whenever you allocate, maybe it grows, it would have to reallocate, and you're getting a bunch of system calls still, right? It's probably better than the standard set with all these nodes dynamically allocated randomly, fragmenting your cache and your memory, but it's still not ideal. What if you could just have some type of scratch space somewhere, and you could throw whatever junk that you wanted in there, and you could just clear it at the end and get rid of all of it, right? So that's exactly what an Arena Allocator gives you. It gives you a block of memory. It has you manage the lifetime of that block of memory, right? So maybe at the beginning of your program, you allocate that memory, and this is your scratch space. Throw whatever you want in there whenever you want, and clear it whenever it's not needed anymore. And the clear method is just going to be incrementing the offset, or not incrementing, setting the offset to 0, right? So how would you implement this using the API for my Arena Allocator? It's going to be this right here. So let me uncomment this. Okay, so you have to inherit from it and give it a couple of parameters. Here we're using safety and we're using multi-type. I'm actually not going to use safety. And you create an arena, arena pointer, which is your pointer to your memory right here. Then you create an arena allocator. This is an instance of the allocator that you can pass to the standard library containers, right? If I click on it, it has a member arena pointer. So it's a stateful allocator. Because it's a stateful allocator, you're going to have to pass it into your standard set like this in the template parameters. And then you're going to have to pass your instance right here in this location. So you can give it a proper reference to the pointer. Okay. And then it just works exactly the same as the previous one, right? You're going to notice that you are responsible for destroying the arena at the end, and also that you have to give it a size. So you know the size. What happens, for example, if you give it 5 as a size instead of 512 kilobytes? Wow. What is happening? Yeah, that was a really weird crash. It like... Yeah, that was a really weird crash. I got more explicit crashes before by doing this. But yeah, you're just writing off the end of your heap. And so it's just a crash. Okay. So let me show a benchmark just to see roughly how much faster is this versus the standard allocator. Now benchmarks are very particular. I've actually written benchmarks where I've seen this block allocator, for example, underperform the standard allocator. And then I've seen the block allocator far outperform the standard allocator. Okay, so benchmarks, what are we doing? We are allocating first with the standard allocator here. Just this string, it doesn't matter. We're adding up the string so the compiler doesn't optimize away the work that we did. And we are printing the time. So first we're going to do it with the standard allocator. And then we're going to do it with block string. Block string uses the block allocator. Then we're going to do it with arena string, and arena string uses the arena allocator. All right. So the vector is actually still using new and delete here, or malloc and free, whatever it uses in the background. But the strings that are allocated inside are going to be allocated using the arena allocator and the block allocator. Okay, you can see the standard allocator is the slowest. Block allocator is more than twice as fast. And the junk allocator, the arena allocator, is almost 3 times as fast. So I actually ran some other tests. One time I was just allocating 100,000 integers. It ended up that the arena allocator was 27 times faster than the standard allocator, which is pretty good. I mean, if your frame took... If it was taking up 2 milliseconds of your frame, it would take up less than 0.1 milliseconds of your frame, which is pretty good, I think. And I actually ran some tests. I think I was allocating vectors where the block allocator underperformed the standard allocator. I could never get the junk allocator to underperform the standard allocator, though, because it's very simple. So I expected this arena allocator to be simple, but it was mildly complicated to write. And so I give you a couple of concepts here to give it a couple of flags in order to choose whatever type of behavior that you want. Anyway, initially you got an arena pointer. This is your pointer to your arena, your size and your offset, you know, whatever, your constructor. Deleted moves and copies, because I can't think of a reason to move or copy the arena pointer right now. You know, maybe later I could figure out a reason and I would undelete these, but right now they're deleted. Okay, let's read the comments here just to see what these will do. Arena safety concepts ensures that standard junk allocator receives use safety or no safety. So yeah, these are the two tags that you're allowed to pass in. No safety will cause junk allocator allocate to call unsafe allocating, omitting the bounce check intended to be used with get free slots. Okay, so you get no bounce check if you pass in no safety. The arena single type concept will give you the options, use a multi-type or use single type. This will let you either decide to use a single type with your arena or use multiple types with your arena. And if you use multiple types, there's got to be an extra set of calculations in order to align the pointer, right? So if you use a single type, it's going to be faster, right? And so that's all the user's responsibility. Okay, you create an arena, you destroy an arena, you clear the arena just by setting the offset to 0. That's all it is. Imagine you allocated, you know, 5 gigabytes of integers. All you got to do is set this offset to 0 and they're all deallocated. That is instant. Okay, get free slots. This function is a little bit weird. Basically, it returns the amount of free slots there is in the arena. So you pass in the arena and you give it a type and it will tell you how many objects of that type can still fit in here. Uses a little bit of weird math. Took me a little while to figure out how to get this working properly because I didn't want to calculate any of this at runtime. But yeah, if you got a power of 2 type, you can actually shift it right instead of dividing in order to get your answer, which is going to speed up the function quite a bit. Okay. Down here, this is for multiple types, and this has to consider the alignment of the pointer. That's basically it. Allocate. Notice all allocate does is it takes the size, it checks if there's enough size, and if there is not, it gives you back null pointer. Then it finds the next pointer just by calculating the offset into the arena. It updates the arena offset, and it gives you back the pointer. No dynamic allocations. Really, really basic pointer arithmetic. And it's just insanely fast to allocate. Okay, unsafe allocate omits the bounds check. So it's slightly faster. Multi-type allocate, you have to align the pointer, which uses a little bit of weird bit twiddling right here in order to get that pointer aligned. It's pretty magic when I figured out how to do that. Okay, this omits the bounds check. Construct will call allocate, but it will forward all your construction arguments, and allocate will and it'll placement new all the types. So if you got like a non-trivially constructible type, then you can construct it using construct, or you can just get the memory back, the pointer back, and you can placement new yourself and do that to construct a type. Okay, unsafe construct, same ideas. It calls different allocate functions. And destroy gives you a function to destroy the objects that you allocated. Right, so the Arena Allocator doesn't have any method to destroy the objects. That's all your responsibility, to destroy it. So whenever you allocate something that is not trivially destructible, just call destroy on it, and that's it. Okay, this is a wrapper for the standard library. Couple of random stuff here. It just calls junk allocator for its methods. Here, based on what flags you type or that you pass in, right? So if you pass in use safety and use single types, well, then it's going to give you allocate, and otherwise unsafe allocate, multi-type allocate, or unsafe multi-type allocate. Deallocate is a no-op. So when a standard vector or standard set goes out of scope, they will call deallocate, and that's going to do absolutely nothing. It's your responsibility to deallocate. And the comparison operators just compares the arenas. That's it. That's the Arena Allocator. Relatively simple. Just some offsets into a heap. And it's insanely fast. You should really write your own Arena Allocator right now.